Today I'm going to be talking about Lab 2. My name is Noor Yusuf. For my introduction, I'm going to start with purpose and assumptions. The purpose of this lab was to track the motion of an eraser to observe the changing position and velocity, as well as compare real-world findings to two computational models, one that does consider drag force as well as one that does not consider drag force. The major assumptions of this lab was that we're only observing the y-axis movement of the object and ignoring any other axes. And we are also going to neglect the height between the horizontal ruler and the ground, as we had to throw it from above the ground. A preview results is that we can obtain that freely falling objects on Earth experience a drag force that doesn't correspond to how an object would fall in a vacuum as terminal velocity is reached. The fundamental physics principles that we will use is that the velocity is changing, which means that our net force on the object is not zero. We'll also use our velocity update formula as well as our position update formula, which are both on the right respectively. We'll also use our gravitational force formula, which is mass times the gravity near the surface of the Earth, which is calculated on the right, as well as our general gravitational equation. We also use drag force, and drag force is opposing the motion of the eraser and increases in magnitude as time goes on and the velocity increases. The formula for drag force is below, and we can see the what I just described in our free body diagram. The system is the eraser, and the surroundings is anything outside the object that might affect its motion or interact with it, such as air resistance, an initial push, or the Earth. The initial conditions is that the ball has no velocity and the ball has no initial acceleration, and that the standard indoor air resistance is observed. Details of the experiment is that we threw an eraser, we had a ruler to show the horizontal distance as well as the vertical distance, and we threw the eraser about the height of the vertical distance, and we tracked the motion using tracker and created resulting graphs, as well as using computational models to create predicted graphs. The materials we used are an object, which is an eraser, a timer, and a ruler. For my tracker analysis, here's my video. You can see on the right for the graphs that the position follows what we expect for the position, and that our velocity is constantly increasing. For a computational model, we had two, one with drag and one with no drag. For the one with no drag, we set our mass to 0.04 because that's our mass of our eraser. We have our initial conditions with our position being 0 and our delta t being in increments of 0.01. We can see that our magnitude of the acceleration due to gravity near the Earth's surface is 9.8, and our proportionality constant is 0 because there's no drag force. Which means we just apply the momentum principle to update position and velocity. We first update velocity using Fnet, which is just gravity, which is 0 minus mg, and the position of the ball. And then update the position of the ball. We then do the same with drag, except the initial conditions are pretty much the same except for a proportionality constant, which is 0.01, because we now have drag, which causes us to have to calculate the net force, which is going to be the force of gravity plus the force of drag. The force of drag uses the equation that I mentioned in our introduction. After obtaining the net force, we would update the velocity update formula and then use that to update the position of the ball. Here are the results of the computational models. You can observe that they are pretty much the same except for the one without drag goes a little bit higher on the y-axis than the one with drag. Comparing all three, the tracker, the two computational models, you can see our experimental in blue, our computational model with drag in orange, and our computational model with no drag in green. We can see that there's an observed and predicted position. The observed and predicted positions follow similar changes in position, and that the computational model that doesn't consider drag and the computational model that does consider drag begin to deviate greatly from each other, which means both graphs greatly overestimate the position, likely due to error. The angle of the possible errors was that the angle of the video was recorded. The angle of the video that was recorded in, it could have affected the results as it wasn't 100% perpendicular. And our differences in the placement of the cursor while tracking the eraser, as well as rounding errors, or not having a small enough delta t, which could have led to not enough points in tracker, or not putting in the correct drag coefficient. Some discussion questions to consider is if that we were to examine the velocity versus time by predicted by our models, with and without drag, which of, if any, would predict the terminal velocity, and what does this mean? The model with drag would predict the terminal velocity as the air resistance starts to balance out the net force, with the gravitational force. Therefore, we are achieving an equilibrium of forces that allows us to observe an almost constant velocity. That plateau as the acceleration goes to zero. And if and we also consider what if the terminal velocity doesn't depend on the initial velocity. We can conclude that the terminal velocity reached earlier and is constant. Thank you.